Right, okay, hello. Welcome to the finale, the final lesson, part 6 of our A-level look at waves. So we started 6 lessons ago, we looked at progressive waves, longitudinal transverse waves. We had a hardcore lesson in refraction and total internal reflection where we went through Snell's laws, superposition of waves and stationary waves. Our last lesson was interference, looking at constructive and destructive interference between waves. And the final one today is diffraction, which is kind of a continuation really of some of the things we were looking at in interference in terms of Young's double split and the single split techniques as well. So, diffraction. As we talked about before, about way back in key stage 4, diffraction is basically when a wave passes through a barrier, through the space in a barrier, and the waves are disturbed or they diffract out. Now this is actually showing, although this is one large part here, there are lots of little mini spaces in between. So this is causing lots and lots of diffraction, and this is meaning that there is that interaction that we were saying before, the interference between those waves, which is making some of them constructive, like we had here with our double maximum, like we were talking about in our previous lesson, and also results in our dark spots here where we have destructive interference, where the waves are completely out of sync with each other and they destruct. So that at one point there is the top crest, and at the same point on the other wave it is the trough, so they cancel each other out. And then we get our other waves, which are just our normal light waves coming out here, which are not interference, or they are normal, they have interference that just still results in a normal wave amplitude. So therefore remember, our double maximum is twice the intensity. The light is generally twice as bright, it's said to be twice as bright anyway, because it has this constructive interference between it. So with the single source, this basically just brings us one there, and it only brings us a few dots. But with our double, with our Young's double slit experiment, this brings us out with twice as many diffractions from each point, and those interacting with each other means that there's a lot more interference going on, which means we resulted in a lot more of these fringes, or the distribution of these fringes as we were talking about in our previous lesson before. So you get your fringes of light, and then our fringes which are light, which is our constructive interference, and then our dark spaces, which is our destructive interference. And then you can end up with, especially with white light, you end up with the splitting of that light. And this really shows exactly how it works. Now what we're going into here is what's called a diffraction, or called diffraction grating, or diffraction grate. Basically, what it is that you have a material, because generally what they started off making them out of was glass, but these are really expensive. So they started making them out of perspex, which is obviously a much cheaper alternative. And the way it sort of works is that you have your standard light waves coming through, they're going in this direction. I probably should have written them the other way around, but I've done it now. So you've got a pane of glass, and obviously it's plain on there, but on this side what you have is a series of lines that are gouged into the glass. And these lines are very fine lines, and depending on how many there are per millimetre, depends on how fine obviously the grating actually is. And what this actually does is it causes the waves themselves to diffract out from there, and what it gives you is the same as it would diffract out of any other normal space. It gives you your lines of interference in between as they come back out. But what it also actually gives you is your orders of light. So what we're going to do is these orders of light are exactly the different wavelengths of the light coming out at different places. So there's diffraction, as this actually picture this shows here. This is where the white light is, some of the light beams are actually travelling straight through. As we were saying before, with diffraction, is that some waves just travel straight through and they don't get diffracted, but other waves obviously are constructive or destructive. But with the diffracting grating, what it can actually do with white light is it splits it back out again. It does that dispersion to a much greater way, a much more efficient way than Young's double split did. But what it actually does is, with a higher frequency, with the the shorter the wavelength, so there's a higher frequency, actually the less it's bent. So it's actually opposite to when you do dispersion of white light through a prism. Where we said that obviously ultraviolet light through a prism bends more, with diffraction grating it actually bends the least, and it's the red end of the visible spectrum that actually ends up diffracting a lot further away from the centre point. So here is an example of how it works, of how the grating works. And what you end up with is your white light. So our white light source will be coming through over here. I think the next picture is actually a little bit better. We've got white light coming through here, and this is our diffracting grating piece of glass. I think this is actually a glass one, this one. So our white light is travelling straight through here, and this is the zeroth, or what is called the zeroth, or the zero order. So the white light that's travelling straight through. And then what you can see here is where the light split out. This is what's called the first order of light. So this, in this dark area, what we have is the deconstructive part of the waves. So the waves are all being deconstructed at this angle out of this diffraction grating. So there's no light here. And this first order here is where the light is starting to go through and travel through, and either being diffracted constructively or actually just being diffracted out. So a bit like the dispersion. So this is where our first order, and then you can see again we have another dark area here. I don't know if you can see this bit here. This is the second order. This is where the light again has been dispersed out or refracted out into its different sections again, into its different colours. So what we can actually do is, if you know the wavelength, then you can work out the placements of the orders of these lights. So you can work out that angle at which these orders are actually going to occur away from your zero angle. So where you're, again, going back to angles of incidence, so this would be our line of normality. And as long as your angle of incidence is 0, then your zeroth order of light will also be 0 and will travel along that 90 degrees for the fact that angle of incidence, or that line of normality, will stay the same. So then all you're doing is we're working out the angles of where after that angle you would find your first order of light, so this section here. And then you can also work out the angle for when you would then find your second order of light as well. So what we're going to do is we're actually going to have a go at working that out. So the equation we've got here is d times the sine of the angle is equal to n times by the wavelength. So what does that actually mean? And we'll get rid of my scribbles there, and I've already got it written here. So d is actually the sine of the angle is obviously the angle that we're actually looking for as it comes back out. And d is actually the spacing in between the grating lines. So, you know, these glasses, some of them will have, well, the example we're going to use is actually going to have 500 lines per millimetre. So obviously, you know, the gap in between those is absolutely tiny. All n stands for is the order of light that you're trying to find. So it could be the first order that you're trying to find, or the second order, so which series you're actually trying to find. And again, we've got lambda, or my poor attempt at trying to draw lambda, which is our wavelength. So what we want to do is we want to find out our angle. We don't know our angle, but we do know we're going to make up the fact that we know the distance, or the in between the lines that we have on our grating. So obviously we need to rearrange this equation. So we need to divide the d out of this sine angle because it's times by it. So therefore, whatever we have to do on this side, as the rules of rearranging equations, we have to do to the other side. So therefore, the sine of our angle is going to equal n times lambda divided by our d, which is our spacing in between our lines of grating. So as we said, our lines of grating, we're going to have 500 lines per 1 millimetre. So we know that 1 millimetre is in standard form is 1 times 10 to the minus 3. So to figure out exactly what the spacing is, and we've got 500 per millimetre, obviously we need to divide that by 500. So then that will give us our answer of the spacing in between our lines. So again, if you get your calculators out, you need to do 1, and then remember how we did our standard form. You want to press EXP, our exponential button, and then -3. That will give you 1 millimetre with all your zeros, and then you need to divide that by 500, and that will give you your distance in between, which is a lot of zeros and a 2. If you count them, if you count take the decimal point over, we've got 1, 2, 3, 4, 5. We've got 5 zeros, so it's 1 space, 2 space, 3 spaces, 4 spaces, and the 5th space takes you between the 0 and the 2, and the 6th space makes it actually a 2. So therefore, that's 6 spaces we've moved. So our answer is 2 times 10. And remember, we've gone the wrong way, so it's going to be minus. So it's 10 to the -6, because we've gone from having a really, really small number to a big number. So therefore, to get back to our small number, it obviously must be negative. We've got to go down. So that is our spacing. Our spacing is 2 times 10 to the -6. Now we're going to take the wavelength again of my laser pen that I've got, because I've only just got it and I love it and I want to do everything I can with it. So we know the wavelength of my laser pen, which is 650 nanometers. So what that actually is 650, and it's a lot of zeros before that. So what it is actually 10 to the -9. So we know the wavelength. So what we want to do is, first of all, we work out where we would find, if I was to put my laser pen through this grating that had the spacing of 2 times 10 to the -6 in between its lines, where we would find the first order of light that comes off of my laser pen. So in order to do that, we must divide our wavelength divided by our spacing, which is 2 times 10 to the -6, which equals, I'm hoping some of you have already worked this out. It's a shame you can't tell me, but I'll have to work it out myself instead. So it's 650 exponential button -9, and that's divided by our 2 exponential button -6, which equals 0.325. Now, helps if I actually write my numbers properly, it'd be helpful. 0.325. So random bit of interesting facts is that the gap here, which is 2 times 10 to the -6, is roughly 3 times the size of our wavelength. Now this 0.325 that we've just worked out, again, it's not really an angle, although we know like it could be a really infinitesimally small angle. Obviously what we've worked out again is the sine of our angle. So if you remember when we were back in previous lessons, we started talking about inverse sine, or inversely signing numbers. And that's exactly what we need to do here to be able to work out what this actually means in terms of an angle. So you take your answer, which is 0.325, and you need to press your inverse button, INV, and then sine. Alternatively, it could be a second function button with the button that has sine -1 on it. Press that, that gives you an answer of 18.96. So 18.96. Technically I should have rounded that to 18.97, but if you forgive me, then I'll forgive myself. So our answer is 18.96. So that basically means that if we pop back here, that where we had our picture here of our white light, if this was my laser pen that we had coming through here, and this this grating diffractor was here, and it had that the same spacing that we had of 500 lines per millimetre, then that would mean that the first order, this first order of light that we're pointing out here, this first order of light here, the gap in between our 0th and our first order of light would be our 18.9 degrees. So that's where we would start to find our first lot of light. So alternatively, as I said before, what we can now do is you can find out where your second one would turn up as well. So all you'd actually have to do is, the only thing that you've got to change in order to work that out is this n, because remember this n just represents the order that you're trying to find. So therefore our wavelength stays the same, and the distance in between the diffracting lines stay the same as well. So alternatively, all you actually have to do, you've already done the division here and you've got your 0.325. So really, all you need to do is take your 0.325, we'll do it down here, 0.325, and all you need to do is just times that by 2, because all you're doing now is looking for the second order. If you were looking for the third order, you times it by 3. If you were attempting to look for the 6th order, which is very unlikely, you times it by 6. But what we're doing, we're looking for the second order. So 2 times 0.325 is obviously 0.65. So again, that is still the inverse. That's still the sine of the angle that we're looking for. So I need to inverse that. So if I take 0.625 and I inversely sine it, then that gives me an angle of 40.54 degrees. So 40.54 degrees is where we would find our second order of light. So again, we go back into my PowerPoint. So therefore, this would mean is that the angle of the second order. Now remember, this second angle is still working from your 0. Okay. Our first one here was 18.9 degrees, and our second angle is 40 degrees. But it's not 40 degrees plus the 18.95, it's 40 degrees from the line of 0. So it would be 40.5 degrees from our line of 0, or our line of normality. Remember, it's not an addition to the previous angles, it's still always working out from that 0 line. So that is how we can work out where these orders of light are, and how if you know the wavelength, you can work out exactly where they would turn up. But also, alternatively, again, you can spin it round. So if you know the spaces and you know the angles, you can work out what the wavelength is. And this is exactly how spectrometers work, or electrospectrometers that are used to determine the different wavelengths of light. And there's a lot of uses in astrophysics to determine the different chemicals of stars, because they all obviously reflect different wavelengths of light. So you can determine all the different materials, the way that we see things. I can see that this is an orangey yellow because it's absorbing all of the other spectrums of light, but it's rebounding the orangey yellow colour back to me. So I know that that's the wavelength. So if I know that's wavelength, I could tell you what that's made of. So the same as with all different chemicals and gases, they have those reflective indexes, which means we can turn back and find out exactly the colours that they're reflecting back to us. So we can find out the frequency of that. So you can find out the frequency of the wave. So therefore you can find out exactly the material that it's made from. So there's a lot of uses of that in astrophysics. So that is our overview of what diffraction is, the double and single diffraction patterns, and diffraction grating, the uses of it, and obviously how to do all the maths with it. That is it for our A-level look at waves. Not entirely sure if there's going to be any more videos, but I will obviously endeavour to put some more up. If you guys still want some, then please leave comments on YouTube or wherever they are. Cheers, thank you very much. I'm Ian McDowell, I'm a student at Bryan University.